Hello and welcome again to the STEMCstudio channel, and in particular to the Geometric Algebra in STEMCstudio series. Very exciting video for you today. We are going to add the final component, the final mathematical object that we are missing in the plane, and that is something which is called a bivector. The bivector is going to represent a kind of area quantity which has an orientation which can be thought of as a kind of spin. Okay, let's get on with it. So here we are in STEMCstudio again. Recall that the last thing that we did was that we renamed our vector class into something which we call a Gibbs in honor of Josiah Willard Gibbs, who was an American physicist who developed a way of using vectors and scalars together that's called vector algebra, and it was very useful for physics, but it actually was very it wasn't so good for people learning physics, at least later on, because it tended to trap people into a mentality that really there are only scalars and vectors. And we're really kind of fortunate that in the 1960s, David Hestenes came along and he revived a subject called geometric algebra. He gave it geometric calculus, which really kind of completed it. And now we get to benefit from it. Okay, so our intermediate quantity, which is called a Gibbs, which is currently can be either a scalar or a vector, okay, is soon going to be expanded to be able to communicate the full range of mathematical objects that exist in the two-dimensional plane. All right, so here's our Gibbs. Let's run the program. Let's hide the documentation, and we'll just kind of clear the decks a little bit. We'll get rid of some of these calculations that are happening down here. Make a bit of room. A lot of print lining going on. I don't think there's any need for much of this at all, actually. Let's get rid of everything except A. We don't really need that. Get rid of all of these. So we've still got A on the screen, and A, as you can see, is the vector which is 2e1 and 0e2. So 2e1s and no e2. So we have a nice geometrical description of our vector. And in the scalar slot, you can see that the scalar part is 0, as it should be. I mean, if we have a vector, we should definitely not have any scalar part. Okay, let's kind of add another vector to this picture, which we will call B. And we'll make B to be something like, let's say, 1e1 plus 2e2s, something like that. Okay. Print it out. B is 0 scalar part, 1e1 and 2e2. Let's get a look and see what that looks like on the diagram. So we'll uncomment this, and we'll put B in this place, and we'll put B there. Just make a little room for ourselves here, and let's hide the Explorer. There we go. And we'll put B in here. Okay, let's take stock of what we've got. We've got A, which is 2e1 and no e2s, and we've got B, which is 1e1 and 2e2s. Now, what we want to do is we want to really kind of like create some kind of an area quantity that we call a directed area or an oriented area. In other words, it has a sort of sense of rotation about it. And you can see from A and B here that, we don't know, should we go up B first and then go along A, or should we go along A and then go along B? And it matters as to which one of these things that we do when we try to consider the area of the parallelogram that is formed by A and B. So let's just do something. What I'm going to do is I'm going to slide B along so it ends where A is. So obviously B has to start at A dot X and A dot Y, and then to actually slide it along, I just need to add these things together. A dot Y. Okay, so there we go. Oops, hit the wrong one. Okay, format that. And what I'm going to do is I'm actually just going to kind of add a couple of little line segments on this diagram so you can see what I'm talking about. So I'm going to go board.create, and I want to add a segment. So there we go, segment, and this segment is going to go from, the first one's going to go from 0, 0 to where, let's say, B would be if we'd started from the origin, and that's the point 1, 2, but of course it's just B dot X, comma, B dot Y. Okay, all right, got that right. We'll just, okay, that's all good. And then we'll also draw the segment along the top. So that's going to run from where B would have started, B dot X, B dot Y, and then it's going to, we're going to have to add A dot X plus that and A dot Y plus that. Okay, so we've completed the parallelogram. Okay, so what we're trying to do here is we're trying to create something which sort of represents an oriented area. Now, what's the sort of direction? Is this area rotating to the left? Is it counterclockwise, or is it clockwise? And you know what? I'm going to just actually put something else on this diagram. I'm going to create an arc. Don't worry too much about how I'm doing this, although you should obviously take note of kind of like just how easy this is actually. Okay, so to create an arc, you need 3 points. What I'm going to do here is I think I need a kind of want a function that will give me the starting point. Give me the various points given given real Gibbs is coming in here. So let's try and do that. So I'm going to create a function, and I'm going to call it coords. It's like, give me the coords. It's going to take a G, which is a Gibbs. Okay, so this is our vectorish thing, and it's going to return an array of numbers. In fact, it's going to return 2 numbers, and so I can kind of like make that really kind of like concrete there. So I could have written number and then square brackets. That would be an unspecified number of numbers, but this will actually give me exactly 2 numbers. So I'm going to return an array, and it's going to contain g.x and g.y. Okay, so hopefully this will be a more useful function. So for example, before I do that, let's just kind of like test this out a little bit. So for example, our segment here, the second segment, which is intended to go from here to here, I could say this is actually the chords of B. Okay, and then this second part is the chords of A plus B. Okay, cool. So, oops, keep it running. So this is, as you can see here, we're kind of like, this is nice because our code is sort of looking a little bit more geometric in here. Okay, so I want to create this arc, and I'm going to create the arc, I think, the way the arc works. And I'm going to check the documentation here. So we'll go to JSX graph. That. Go look at the API reference, go look at an arc. So the way you create an arc is you create 3 points. P1 is the first point, which is this sort of center point, and the other one is the 2 points. So, okay, so the first point is the center point, and then B is the sort of the from point, and then the last point. Okay, so over here, our initial point is going to be chords of, and what we're going to use here is actually A plus B divided by, rather multiplied by 0.5, because we don't have a yeah, there we go. We want that. Next one we'll go times 0.4, say, and then the next one we'll go to say 0.6. Okay, I'm just sort of hacking this along a little bit, and okay, the downside of this is that I don't get control of my these points here. So, well, I probably do actually, but I'm gonna just do it like this: const p1 equals A plus B times 0.5, and then I can put P1 in there. I'm going to do the same now for P2. No, let's do this again. Let's do a little do-over. Let's try it this way, okay? All right, here we're going to get it right now. We're going to create a point on the diagram, and it's going to be at the chords of A plus B, A plus B, multiplied by 0.5, and then we'll use that. That'll be our P1. Is that? And just format, clean up a little bit. We're going to create P2 and P3, very similar. P2 and P3, and this is multiplied by, what are you doing? 0.5, 0.4, 0.6, okay, and then we want to have P2 in the second position. We want to have P3 in that position. What we want to do is we want to now hide each of these. Here we go. So we've hidden the first one. Let's hide the second one. Let's hide the third one. And then finally, let's give our arc the property that the last arrow, which I could actually hit Control Spacebar here and get last. I should get last arrow. Oh, the reason why it's not working is I've missed my square brace there. I mean, you can only ask this to do so much, right? Now we're going to get last arrow. There we go. Last arrow, true. And yeah, we've got it. Thanks for bearing with me. Okay, so this is what we're trying to do. We have the vector A. We follow A first, then we follow B. And we're not adding them together, but we want to kind of create a kind of a multiplication that will give us this area, the area of this parallelogram. And the orientation is going to be left-handed or anti-clockwise, just like this. Now, if you think about it, this is this quantity that we're creating. It has an area, so it could be thought of as being a multiple of the area of E1, and then follow that by E2. Let's see if we can redraw E1 and E2. It means that we need to slide E2 over to the point 3 minus 3. So we need to put a 3 there and a 3 there. I should, again, I should kind of like be more coordinate friendly and use my more coordinate free and use my own chords function down here. That would kind of like help a little bit to try and do this. But here's the idea. This thing here, this area down here is is a unit of area. It's an oriented unit of area, and this quantity that we have up here is a multiple of that. In fact, if you know that about sort of resizing a parallelogram, you can just slide this over, or you can see that the area down here is the same as the area here by similar triangles. So in fact, this thing is actually 4 units of area, or at least it's 4 units of these quantities of these areas. Okay, so that's the idea. Now, what we want to do is we want to create a way of building this area quantity out of 2 vectors. So what we want to do is we want to do something like this. We want to kind of like go const, and I'm going to call it big B equals A, and then we're going to use a symbol, and the symbol we use actually is like a wedge. We want to put that wedge between, and we will end up with a quantity which we'll call B. Okay, so let's print out B. And something a little wrong. Oh, there we go. So B at this point in time is, well, apparently it's just 0. And that's because we actually haven't defined this, this operator yet. So let's think about this a little bit. We're trying to create a quantity that represents the area. And so we could say that if you had A and then it was followed by A as a parallelogram, that would be just kind of like a line down here. Or rather you could imagine sort of, well, yeah, it'd be like a collinear line, and that would have no area. So intuitively, we can say that A times A, for any vector, A times A is 0. Let's bring out our README file just to sort of summarize this. So we can say A wedged with A equals 0. Okay. And actually I'm gonna just enhance the MathJaxy part here, just so that I don't have to sort of repeat that A is in fact a vector. It's not a scalar. So given any vector, so for any vector $$$$vec A, for any vector A wedge A equals 0, right? Because this is this wedge between 2 vectors is what's going to construct our area. Okay, let's go look at our diagram again. I'm going to hide the, let's see, we'll just hide the code here for a minute. Okay, so if I was to go along B first, so imagine B was over here. If I went along B first and then I went along A, I would get an area which has the opposite rotation, and we want this to have like the opposite sign. Okay, so how could we say that mathematically? Well, let's bring back our code. So I think what we want to do is we want to say for vectors A and B, and we'll improve this, we want A when wedged with B to be the negative of B when wedged with A. Okay. And again, I could kind of like put these whole things in the full LaTeX lingo. So let's just do that. It won't take me too long. A there, B wedged A. Okay, and then the same thing for B. So put B in there. right, how are we doing? There we go. This thing needs for any vectors $, $, $, $, $. Okay, there we go. For any vectors a and b, a wedge b is the negative b wedge a. We should really put periods on the end of these sentences. Hopefully it won't confuse people with periods and stuff. All right, so good. But we know, okay, great. So we know that a is 2e1 plus 0e2, or in general, a can be thought of as being this sort of linear combination of x times e1 and y times e2. So what we should be able to do is we should be able to get a sort of an expression for these things involving sort of wedges. So let's take a look at that. So we want $, vec a when wedged with vec b should be equal to, okay, and let's see if I can pull this off. I want ax, so I'm going to put parentheses around here, and then I'm going to say a underscore x e underscore 1. Okay, okay, and underscores, by the way, they don't work in directly in the README file, because underscores normally are used to create emphasis. So you have to escape the underscore with a backslash to just let the system know that what you mean here is actually an underscore, and to not to treat it as like an emphasis. AY times E underscore 2 a backslash underscore y. So a wedge b is equal to ax e1 plus ay e2. And we're talking about a general a and b here, not the particular a and b that we're dealing with in the diagram. Wedged with, so wedged with, and obviously I can kind of reuse what we've got here. Oops, did something wrong there. Let's select it again. Control C, and then Control V. And what I want to have here is bx and by. All right, and that is equal to, okay, now to actually expand this, what I'm going to need is a distributive law, right? I need to basically have a rule that says you can break this up into this bit wedged with all of that plus this bit wedged with all of that, right? So that's a distributive law that we need. And then to go even further, we're going to need a distributive law that works the other way, which says that a quantity like this, when wedged with that, can be broken down into this wedged with that plus this wedged with that. Okay, so we're just going to assume normal distributive. I'm not going to dwell on that too much. So, you know, what that means is, if you remember sort of the acronym FOIL for expanding out these sort of binomial, I think they're called binomial products, then we're going to be able to take the first, like this thing wedged with that thing, plus outers this thing wedged with the last one, inners this thing wedged with that, and then, you know, last this thing wedged with that. And then what we'll end up with is, all right, this is going to be fun. Okay, so we need like that. Okay, so we get an AX E1 multiplied by a BX E1 plus, and then we just kind of like keep on getting lots of different terms, right? So there's our first term. Let's just check that. AX E1 times BX E1 plus, and now what we want to do is we need the outers. So we need another AX E1 multiplied by, so AX E1 times a BY E2. So here's BY, and there's E2. Okay, so far so good. And then we need to also add, okay, and then this time what we need to do is the inners, so we need an AY-E2 times a BX E1. So we need an AY-E2 times a BX E1. Okay, AY-E2 times a BX E1. And then for the last term, we need an AY-E2 times a BY E2. Okay, let's just hide our code for a minute and just take a look at what we've got there. So we start with A wedge B as we want to try and represent this area quantity here. And we know that A is AX E1 plus AY. This is AX means the X component of A, right? This is the Y component of A. So it's AX E1 plus AY E2, wedged with BX E1, BY E2. We assume distributive laws, so we can go AX E1 times BX E1. That's that term there. Then we go outers, AX E1 times BY E2. And then we have inners, yeah, AY E2 times BX E1. And then the last is AY E2 times BY E2. Now what we want to do, oh, and I need to have wedges in here. I've forgotten my wedges. Okay, so let's make sure that we wedge. So AX E1, BX E1. Oops. Yeah, sorry. I want to put in a wedge there. Yep, that's good. And then that plus that wedged with that plus AYE2 wedged with BXE1 plus AYE2 wedged with BY. Okay, let's get rid of that. Okay, did I get it right? So that wedge with that wedge with that wedge with that, and AY2. Great, and that is going to be equal to, and now what we need to do is we need a rule that can bring this scalar quantity, this bx, this coefficient, and we want to bring it out to the front. And then we're going to be left with a quantity E1 wedge E1. Similarly, we'll get AX BY times E1 wedge E2. We'll have AY BX E2 wedge E1 and AY BY times E2 wedge E2. Now, before we just write all that out blindly, let's just recall that for any vector, when we wedge it with itself, we get 0. So actually this term is going to be 0. Similarly, the last term is going to be 0 because in this term we've got an E1 wedge E1, so that's 0, and here we've got an E2 wedge E2, and that's 0. Okay, now what about these terms? Here we've got an E1 wedge E2, and here we've got an E2 wedge E1. Okay, so when we get the scalars out the way, we could use this rule, and this one will have a minus sign, and then we can convert it into an E1 wedge E2. So what we should be able to do is we should get, this should finally equal AX BY minus AY BX multiplied by E1 wedge E2. Let's kind of like do that. So this thing is equal to, and we'll put this bit in parentheses, and we want to have, we're looking for an AX times a BY, AX times BY minus an AY times a BX. And then this whole thing is going to get multiplied by an E1 wedged with an E2. Let's see if we got that right. Okay, so I'm going to hide the code. Let's check it out. So we've got AXBY, that kind of came from here, the AXBY, multiplied by E1, E2, because we got an E1, E2 there. And then here we've got minus AYBX, and then E1, E2. And we got the minus sign because we were able to flip these two guys from here and turn that into an E1 wedge E2. Okay, so in summary, if you look at this, what we've got is when we wedge together A and B, the result is this number times this quantity here, okay? Right, and what is that quantity, E1 wedge E2? Well, it's this area here that's inside this square. That's what E1 wedge E2 is, all right? Which is an oriented error. It's got a rotation this way. And it's got a magnitude which we don't exactly know yet, because remember with vectors that we don't really know absolute magnitudes yet, but we do know kind of relative magnitudes. And what we can kind of like say is that the relative magnitude of this A wedge B to this is A wedge B perhaps divided by E1 wedge E2, which is this number here, which is a scalar, okay? So that's the theory behind how to construct an oriented area from two vectors, okay? So you have to let that sink in a little bit, but let's kind of just go through it one more time. We want to say that if you have two vectors and they are in the same direction, then there will be no area. So if B was basically flattened down to here along this line, there would be no area. So we require this to be true. We also want to say that if instead of going along A followed by B, creating this circulation, we were instead to go along B and then A, we want it to have an opposite sign, but the error is otherwise the same. So that would introduce the minus sign. So these are our kind of rules. Now what we're going to do is we're going to calculate what A wedge B is in terms of its components, okay? So in terms of the components of each, because each one's a vector. So we do that. We know that we need a distributed law. And actually, I might as well point out here, we're going to assume, I say normal, sort of standard. What is this? Scalar multiplication commutes. Okay, so that basically means I can take my scalar, like this. So we assume standard scalar multiplication commutes, so we can basically reverse the sort of, we can pull this scalar out. And that's actually a total reasonable assumption. Actually, we're kind of like defining it to be that way, and we get this result, okay? So what we can say is that when we wedge two vectors together, we get some number times this quantity. Well, what I want us to do is I want us to think of this quantity here as a new kind of I won't call it basis vector, but like a basis bivector in our Gibbs quantity. Okay, and so and then we can have a certain amount of it. So let's go and try and implement that. Maybe you'll see a little bit more about what I mean when we go and try and implement it. So what I want to do here, let's get rid of the documentation. In fact, let's not even run it right now. What I want to do is I want to add another quantity to our Gibbs, and I'm going to call it B, and I'm just going to add it just as I would have done like a scalar. So I'm going to go public read only B is a number. Okay, and just like before, we are going to get errors that we need to sort of fix up, right? So the way it works is it works just like the scalar stuff. Okay, the B quantity is the amount of this oriented area. Now, vectors don't have an oriented area, right? So it's going to be 0 here and 0 here, right? There's no oriented area quantity, just as there is no scalar quantity, okay? And then to make this just compile, I'm just going to put in a 0 here, but obviously there's maybe more to be done in here, just like there was more to be thought about it in here. We haven't done that yet, okay? Let's just make everything work as it did before, just by adding zeros, because we know that basically what we were creating before were vectors and scalars, right? And we will fix this all up. Okay, so we've done that. Everything is compiling and running again, and then we can run it. It should not change anything, right? Everything just works as it did before. But now what we want to do is we want to actually incorporate a sort of a way of actually computing the wedge product into our Gibbs class. So I think one other thing I should do is I should find the Tostring method, and I should complete that. So we need to add on $this dot b multiplied by, and what we're going to be multiplying it by is e_1 wedged with e_2. The 2 here is a little subscript. Okay, so let's see, how did that kind of like come along? Well, A is no scalar part. It has a vector part of 2, nothing in the E2 direction, and no amount of area. Okay. Similarly for B, it's got a component in the E1 direction. It's got a component in the E2 direction. It has no area, has no scalar quantity. Okay. So far so good. Let's go back to this thing, and we're trying to build out this wedge so that we get something. Again, let's kind of like follow the path that we did before. So instead of doing this right away, let's try and do this. Let's do const b equals a dot wedge. Okay, so capital B is a dot wedge b, and b doesn't obviously exist. Wedge doesn't obviously exist. Well, actually, I'm going to give it a different name. This product that we're creating is called either the wedge product, which is kind of like a sort of nice user-friendly way of calling it. And it reminds us of the little wedge symbol, but more officially, it's called the exterior product. And I like to use ext as a way to do that. Okay, so let's use ext. All right, so where would we put this? Let's kind of like put it in alphabetical order. So we want to create the exterior product with the right-hand side being a Gibbs. Okay. And it's going to return a Gibbs, because a Gibbs is able now to return scalars, vectors, and also something which, you know, has this area. And we need to compute this thing. Okay, so this is where the computation is going to be kind of interesting. How do we do that? So we know we're returning a Gibbs, right? Let's say that the two things that we're dealing with are vectors. So if they're vectors, there will be no scalar quantity. There will be no vector quantities, but there will be an area quantity. So let's go const b equals, and now we need to just kind of like refresh ourselves of our of the formula that we have here. It's going to be ax, it's going to be the left-hand side's x multiplied by by. So it's going to be this dot x multiplied by the right-hand side's y minus this this dot y multiplied by the right-hand side's x. Okay, and it says b is declared, but it's not used, not read, so we need to drop that into the slot. And we've only calculated here, you know, the exterior product of vector with a vector. So again, this is our poor man's exterior product, but nonetheless we've done it. So let's kind of like just take a look at the results here. We're going to hide the documentation, and we've got b is 0 scalar part, no vector part, no vector part in the E1 direction, no vector part in the E2 direction, but it's 4 lots of E1 wedge E2. That's kind of cool, right? So, you know, we're getting there. Let's try and make our notation here a little bit more natural. So instead of doing this, I want to do, you know, what we've kind of already got here. Okay, I'll just put it below for the time being. I want to do something that looks more like that. Okay, so to find out what that should be, let's go and take a look at the documentation again. Go to the user guide. Let's look for operator overloading. And for overloading this symbol here, which we call the exterior product, we need a method that's called _wedge. Okay, and we'll come across how we used the right wedge soon. So let's come back to this, come in, we'll get rid of that, which is the documentation. We'll run the program. Okay, so we've replaced our a.ext b with a wedge b, and as you can see, we're getting sort of nonsense again for b. That should contain a 4 E1 E2. That's because we need to implement the wedge. So we'll come in here, and I think an appropriate place to do the wedge will be somewhere down here. Now, the wedge is actually going to work pretty much like the mul, but I'm not going to implement the whole thing until we really need to. So we'll do wedge, where the right-hand side is also a Gibbs, and it's going to return a Gibbs. All right, and we know that we've already implemented the wedge product, so that's just called ext. So it's return. We need to return this dot exterior product with the right-hand side. Okay, that's gone away, and we've got b is all this lot plus 4 E1 E2. Okay, so let's just format that. Let's just take stock of what we've done. We'll just hide that. Okay, so what we've done here is we have implemented a product of 2 vectors. Okay, this is not normal multiplication. This is a special kind of multiplication called the exterior product, where we take a vector A and we wedge it with B. In fact, let me go and change this to say A wedge B. There we go. A wedge B is that. And in fact, we could also do A, or rather B wedge A is B wedge A, right? Let's check that. B wedge A, 0 scalar part, 0 vector part, but a negative for E1, E2. Never mind, it says plus minus. That's because our two-string method is not very sophisticated right now, but it's really just minus for E1, E2. Okay, there was a lot of theory in this, I suppose, when you look at kind of the when you look at kind of what we did here in preparing for this. But actually, if you look at this and you were to substitute kind of like put a multiplication symbol in here, it wouldn't be true, obviously, because multiplication doesn't work like this. But we've done nothing that's any higher than just ordinary high school algebra, right? It's like we've really done nothing special, and yet we've kind of like come out with this rather interesting product, which is able to describe our parallelogram. Some of you might also recognize that this quantity ax by minus ay bx, that it actually does look a little bit like the area of this parallelogram. If you were to actually kind of like calculate it, then you would find that this thing is starting to look like the area of the parallelogram. Although it actually really, it's the ratio of this area to the area of this little square here. Okay, to be precise, because we can't do absolute magnitudes yet. Okay, so I'm going to just say, let's finish right there. And in the next video, what we will do is we'll come back and we'll just start to sort of tidy things up a little bit. But, you know, something pretty amazing has happened here. We have now got a quantity which can represent scalars, it can represent vectors, and it can represent areas in the plane, okay? And this is going to enable us to actually represent any physical quantity that would happen in two-dimensional physics. Scalars, it would represent mass, charge, things like that. Vectors, we can use it to represent forces, momenta, velocities, linear momenta, and then the rotational part, we can use that to represent angular momentum, angular velocity, torques, things like that. And you'll find that all of these kind of like fit together in an unbelievably beautiful sort of elegant way. Okay, so, you know, we've got the code here. It's, you know, it's kind of like, oops, the code for our Gibbs. It's a little bit messy. It's very incomplete. But it's kind of like starting to do some interesting things for us. Now, one final thing here is, you know, we're going to sort of knock Gibbs off his perch. Gibbs gave us this kind of idea that we can do a lot of algebra in 3 dimensions, okay, really 3 dimensions, by staying only with scalars and vectors. And the reason he was able to do this was that he was able to sort of fake this rotating object by considering the vector that was perpendicular to it, right? So, you know, whereas in the plane you have a rotating object, and, you know, that's how you describe your angular momentum. What Gibbs would say is we can describe that by using the perpendicular vector. This only works in 3 dimensions, so it's not going to work in 2 dimensions, 1 dimension, 4 dimensions, and you know that physics, at least the most natural place to consider physics is 4-dimensional space-time. And then the string theorists will be telling you to think about, you know, much higher dimensions than that. So we're going to knock Gibbs off his perch right now, and we're going to turn this, we're going to rename the symbol, and we're going to give it its proper name, which right now it's called a multivector. Okay, so why is it called a multivector? Okay, why many vector? Okay, well, there are 3 kind of parts to this vector. I mean, you know that there are 4 coordinates, A, X, Y, and B. But the X and the Y are 2 vector coordinates. So if you think about it, we've really got 3 kinds of things. We've got scalars, we've got vectors, and we've got bivectors. The area quantity is made out of two vectors. Okay, if you think about it this way, we can say the scalar is made out of no vectors. So we've got a quantity which is made out of no vectors, a quantity which is made out of one vector, and a quantity which is made out of two vectors. So the whole thing we can kind of call a multivector because it's made up of these different kinds of vectors. And that number, the dimensionality, like 0 for a scalar, 1 for a vector, 2 for a bivector, in addition to being the sort of the dimensionality of the subspace of those things, that we also call that the grade. So a scalar is a grade 0 quantity, a vector is a grade 1 quantity, and a bivector is a grade 2 quantity. Okay, so that's just a little bit of terminology. Okay, we're not going to call it, so I like to call these geometric quantities geometric numbers, but I'm not going to call it a geometric number yet because we still don't have any way to measure the magnitude of areas. We can only do relative magnitudes. Okay, so that's it. I guess we need to rename the file too. So we're going to rename this to I don't know, a multivector 2D, mult2D. Okay. We could also call this file just math, but let's kind of call it mult2D for right now. So we'll rename the file mult2D, and as you can see, that's renamed it here. So we've got a multivector which is in the file mult2D. Okay, so a lot to take in there. Go and play with it. Try things. You might find little things that are incorrect from the point of view that we haven't implemented them yet, and you might want to try to do that. Experiment with that, but we're going to fill in all of the details. What we've got works, it's just not complete yet. Okay, so I hope you enjoyed that. It's exciting. We've got this like really powerful number. It's just going to get more powerful as we introduce the geometricness, the ability to measure. Okay, if you like the video, hit the like button so other people can find it, or subscribe if you want to be notified of any future videos. Take care again, and happy coding. Bye-bye.